Hello everyone. Today we'll start our discussion with the optical activity. The optical activity is shown by molecules that is chiral. So let's tackle the definition of chiral molecule. Let's assume we have a molecule, something like this. And we need to know whether this molecule is a chiral or not. And by the definition, the chiral molecule is the molecule, it's a mirror image. It's not superimposable to the original one. So if you want to know if this original molecule is a chiral molecule or not, you have to imagine a mirror image molecule. So let's try. Again, you can pause if you want to practice drawing mirror image. Alright, so then you can imagine and try to superimpose them in this form, or you can turn into other drawing form we talked about before, like a Fisher projection, a Newman projection, etc. So say you want to use these drawings, and you know when you flip this molecule 180 degrees, you bring OH over here as well as the methyl group, the CH3 group here, and the Br over here, and this CH3 groups right there. So let's try to draw that underneath. So this one comes here, and OH comes here. However, the wedge line indicates the OH group coming out. So as you flip, it's going in. So OH right there. And then bromine is on number 2. Bromine is on number 3. So that guy is gonna come out. Then there is a number 4, which is right here. Then you slide it over, and you see they're not superimposable. They are all having same connectivity, but spatial arrangements are different, so they are enantiomer, stereoisomer, one of the stereoisomer that is enantiomer in this case. So this proves that the original molecule is a chiral molecule. So this is a chiral. There's a concept that is kind of confusing, such as the fact that you have chiral center right here and here. If that means the molecule that has a chiral center is going to be always chiral molecule, in order to explain that, let me introduce you the concept of chiral center. Chiral center is usually defined as the central atom, chiral center, central atom that has 4 different groups or atoms. So as you see here, this carbon has methyl group and this huge group, and OH and the hydrogen. So this is the chiral center, and that as well is a chiral center. So is this molecule chiral molecule because the molecule has a chiral centers? Well, not necessarily. Here is the example. If I show you this, this molecule has chiral center right here and right there. But if you try, that's not chiral, because when you draw a mirror image, you get this. And then by flipping it, say in this case you flip this way, okay? So if you flip it that way, you get this, and then the BR comes here and that's going to come out, and this BR is going to come here and now it's going to go in, and you see when you compare these two, they're exactly the same, so this molecule is not chiral. And if you draw this in the Newman projection, Fisher projection, you know you should have them in eclipsed, right? So let's have them eclipsed. So here, by spinning around this bond this way, I have these two C3 groups eclipsed, and this stays the same, Br, and there is a hydrogen, and the methyl group comes up. As you spin, Br group will come down and out at the same time, and see they're eclipsed, and another hydrogen here, they're eclipsed. Then you can see there is a mirror going through the middle of the bond, and that reflects each other. So if you give confirmation for that one, Br is heaviest atom, number 1, carbon and carbon, but this one has carbon, bromine, hydrogen rather than hydrogen, hydrogen, hydrogen. So number 2 and number 3 and number 4, then you put the number 4 away from you and you see that is 1, 2, 3, and that is S because it goes counterclockwise. The mirror image of S should be R. You can check it later for yourself, by pausing the video. So this kind of molecule with the same group, same connectivity, opposite stereo center is called meso compound. And you can also draw this in the Fisher projection. Easiest way is having hydrogen away from you as it is, and having these two side groups coming towards you, and this as well. You can show this way and this way in Fisher projection, hydrogen, hydrogen, and CH3 here, and the bromine here, and CH3 there, and you see this mirror reflect. Or you can see the molecule from different angles and come up with a different Fisher, and still have the mirror, and that proves that this molecule is a meso, and meso structure happens to be a chiral compound, not chiral compound. Okay. So, presence of chiral center that has 4 different groups doesn't mean the molecule is chiral. It's very important to remember. That was because some molecule with the chiral centers that have an opposite configuration and they have an opposite effect. So then we are ready to talk about optical activity. The chiral molecule is known to be optically active. achiral molecules are optically inactive. So what is the optical activity? In order to explain optical activity, I have to briefly mention about nature of the light. Light is known as pure energy form, and this is your photon. It is considered as a particle but also as a wave. As photon proceed in the space through the matter sometimes, this shows fluctuating electric field with a certain frequency. Perpendicular to that, we have magnetic field also oscillating with the same frequency. So the electric field increase to the upward for this wave, and after some point, half of the wavelength, the electric field going opposite direction, and that repeats. These are the vectors, increasing and decreasing and changing direction. So if I show you this as photon having electric field around the path it flies through, if you see the oscillation of the electric field from this angle, okay, it will appear like electric field going up increasingly. Some point start to come down all the way to the bottom of this wave, and repeatedly going up and down. So we can say there is an oscillation this way. But in real life, there are bundle of photon flying with many different oscillation. So you can imagine how this is really like. If I have to squeeze these waves here, I can imagine having another wave oscillating this direction, or even this direction, and so on. But we can filter off all of other direction but one direction. Say this is a special material, has a function of filtering off of the other electric field directions, leaving only this direction. Then passing through the filter, you only have one direction of oscillation. That wave comes out. That when you place optically active compounds such as R or S, or the multiple chiral center that is not a chiral molecule, say we have a simple molecule with only R configuration, then when the electric field of the photon interact with the special arrangement of the charges in the space in R configuration, these oscillation of charges in the light interact with the spatial arrangement of the charges in the molecule. This turn, so it gains a momentum to a certain direction. Say it turns this way. So you might now have the photon oscillating that way. Then using another set of filter, we can measure how much rotation it made from the original angle by rotating this filter. We can see the darkness through the filter until you have a appropriate rotation, so the light can come out and that will appear to be bright. And that angle is function of temperatures and other conditions, but if you divide that by the concentration of sample and the length of the sample cell, just like a UV, you get the specific rotation value. That is unique for the compound. If you think about it, this is very similar to Beer's law. When the Beer's law was A equals epsilon times C times L. So this explains why the optically inactive compound that has no distinct structure, which means the original and the mirror image, they are superimposable. They have no optical rotation. However, the chiral molecules have a special arrangement that is different from the other mirror image isomer. They have a different optical rotation. And also that explains why meso compound, although it has the opposite arrangement of the same group with a different polarity and charges, becomes inactive. That's because they cancel exactly. Which means, hypothetically, if this part of the charge arrangement interacting with the polarized light make the polarized light turn, say, clockwise 10 degrees, then this exact opposite of the same amount of charge will make the polarized light turn back to the same degree, the opposite direction. So after passing the molecule, the polarized light appears to have no rotation. However, if you imagine the molecule with opposite configuration, just like the previous example here, sorry about that. Like this case, you have a same S and the R configuration, opposite. However, the bromine and the oxygen cause different polarized charge arrangement on this side and that side. So the polarized light will have a different amount of the interaction, different intensity of interaction. Therefore, they're not going to completely cancel out the rotation. Therefore, this molecule will be still optically active, and also easy for us to figure, to see whether they have a mirror image or not. They're not, because they are different, so they're not meso. So this is another easy way of figuring out without scientific consideration. So yes, chiral molecule is optically active, but the molecule with the two chiral center sometimes is optically active, sometimes it's not. The case is not, the half of the molecule is the same as the other one, that's called a meso. Is there any other way or situation you don't have optically active situation? Indeed, you can think of the case where you have exactly same amount, 50 to 50, of same polarity molecule, such as this, but in opposite configuration, like that. Then this molecule is opposite to that with the same polarity, therefore each molecule turns the polarized light opposite direction, however by the same amount, therefore it will cancel, so the mixture of the two will not appear to be optically active, although individual molecules are optically active. This mixture is called racemic mixture, and those molecules are called racemate, like a roommate to that one. But when these are not in the equal amount, you can imagine they're not making the mixture optically inactive. So there are more details into this. Some reactions that we'll cover in the future generate these mixtures in different ratios. Sometimes it's racemic mixture, sometimes you create different ratio, and the product will be still optically active. So if you assign configuration, this one, bromine is the biggest one, oxygen second, carbon, and then fourth, hydrogen. And that's away from you, so it's perfect. And you connect, you have S, right? S configuration for this chiral center. The molecule has a mirror image right here, and they're not superimposable if you try. And that's going to be 1, 2, 3, and the 4. So connected, it is R. So yeah, they are mirror image and not superimposable. So individual molecule, they are all optically active. However, the mixture in the same amount will make them inactive as solution. Say the original molecule was R configuration, and the reaction gives both of them. Then you say, oh, this reaction makes racemic mixture. If one of them forms more than the other, we say that is stereochemically selective. Selectively make one more than the other. More than the other. If the reaction gives exclusively only one, then we say stereochemically specific. And also, the molecule that has different configuration, we call the molecule has inversion. It went through inversion of configuration. The molecule that has the same configuration, we say retention of configuration throughout the reaction. Alright then. So we can use these optical activity to detect different isomers, because one of the stereoisomer enantiomer if you have enantiomers, it's difficult to tell apart, because like we discussed in earlier video, they have all same chemical and the physical properties. Again, such as boiling point, same, so that makes it difficult to separate by the, say, distillation. They have the same solubility, therefore it makes it difficult to be separated by, such as extraction or recrystallization or column chromatography, etc. However, they have a different property. To the different stereoisomers. And that gives us clue why we are concerned about these stereoisomers, and also how we can separate them. So say you have a protein, very simplified protein, that has a certain polarity and the size of the group A, B, C arranged inside of the active site. Then if you have structure that matches with the B, C, A this way, then this molecule will be able to interact with the active site. However, if you have a mirror image of it, like this, different isomer, then this will not be able to interact with this active site. Therefore, the body uses enzymes for a lot of different activities, and although these two molecules have awfully similar properties, only one of them will able to activate the function of the enzymes in the body. Meanwhile, diastromers we talked about, they have a completely different chemical physical property. So if we want to separate the enantiomers, we have to convert them to diastromers. How do we do that? There are a couple examples that I can tell you. We can make column chromatography built with one of the stereoisomers. Say you have stationary phase of the column or paper chromatography. You can convert the surface to stereoisomers. Same way over here and here. If the stereoisomer has a special arrangement of A, B, C this way, then only one of them is able to preferably make interaction with the stationary phase, thus it will slow down, while the other one that doesn't have a strong interaction with it will move fast with a mobile phase. Allowing them to be separated. So chromatography. Number two, you can have these two isomers reacting with another stereoisomer. Say you have molecule specifically with the E, F, G, H, and they are able to react with these functional groups. However, because of the specific arrangement, say this was S and this was R and the S, hypothetically, after reaction, let's make it S prime because you have S here. If you get the two reaction with R, S prime, or S and the S prime, they are now not mirror image anymore, and they are diastromers. And diastromer has a different chemical physical properties, so we get plenty of different ways of detecting them, and also isolating and purifying them. Okay, so there are a lot more to be said about this experimental skills and theoretical things about chemistry with a polarized light, but we'll probably handle that in different video. So that's it for now, and in next class I'll talk about, as I promised before, the hybridization that gives us more deeper insight about structure of the molecules. Bye.